Okay, thank you. So this is joint work with my collaborators Libor Kahak, Xavier Quattura, and Robert König. And before I talk about the complexity of GKP states, let me maybe recall the more common definition of the complexity of an n-qubit state. So a question that naturally arises in many tasks of quantum info is, given some quantum state, how difficult or how costly is it to prepare the state? And to make sense of this question, we of course have to agree on a gate set, so a set of operations that we allow. And possibly we want to use m auxiliary qubits. And so given some allowed error epsilon, we can define the complexity of this target state as the minimum size of a circuit U over this fixed gate set, such that a reduced output state on the first n qubits is epsilon close. And so in this talk, I want to kind of show how we can translate this notion of state complexity to continuous variable systems, and also demonstrate some techniques how we can bound the state complexity. Okay, so to set the stage, the system that we are considering are hybrid qubit oscillator systems. So systems consisting of, let's say, m bosonic modes and m prime physical qubits. And one of our goals was to identify operations which are natively available in concrete setups, such as superconducting circuits or trapped ions. And so this is like, as an upshot, this is the list of all operations that we want to allow. So as you can see, there are operations only acting on the oscillators, operations only on the physical qubits. But to make the set powerful, we also need interactions that act on both the qubit and the oscillator in parallel. Okay, let me say a few more words about these operations, starting with the oscillator system. So as you know, they're characterized by the quadrature operators, so the position and the momentum on each mode satisfying the canonical commutation relations. And one operation that we need is the preparation of the vacuum state being the unique ground state of the harmonic oscillator. Then we also want to allow Gaussian 1 and 2 qubit, 1 and 2 mode unitaries of constant strength. So these are the unitaries generated by quadratic Hamiltonians and the quadrature operators, and constant strength, meaning that this matrix A that you can see here is just bounded by a constant. So for convenience, we make the choice 2 pi, but for the complexity of theoretic statements, this does not play a role what constant we choose. And importantly, these operations are generated from single mode squeezing, single mode phase-based rotations, and 2 mode beam splitters, so operations that are very standard in any optics lab, for example. And lastly, we also want to use phase-based displacements of constant strength, meaning that the displacement vector is just bounded by a constant. Okay, so I guess the physical, or the operations on a physical qubit are quite standard, so I don't have to explain them too much, but maybe let's say a few words about the qubit oscillator interactions. So what we need is qubit-controlled single-mode displacements of constant strength, meaning that depending on the state of a physical qubit, our mode is displaced in phase space by amount that is, again, constant in the sense that I previously explained it. And importantly, also, these operations are kind of a standard tool in various experimental setups, which are basically described by Jaynes-Cummings type interactions. Okay. So what we want to do now is we say that all of these operations are elementary operations, and we want to attribute to each of them 1 unit of complexity, basically. And so with this preparation, we can finally define the complexity of a CV state. So in this talk, we'll only consider single mode states, but it can easily be generalized to the multi-mode case. So we consider 2 preparation protocols, which induce 2 different definitions of state complexity. So first, the unitary preparation. So we initialize each qubit in the 0 state and each mode in the vacuum state. Then we perform a sequence of these elementary unitary operations. And again, we consider the output state of the first mode, so the reduced density matrix on the first mode. And similar to the qubit case, we we just say that the complexity of our target state is the minimum number of operations we need in order to prepare a reduced density matrix that is epsilon close to our target state. And secondly, we also consider heralding protocols. So these are protocols that require post-processing. So the first two steps are similar to the unitary case. And in the third step, we perform homodyne measurements on the auxiliary modes and computational basis measurements on the auxiliary qubits. Then, depending on the measurement outcome, we compute a flag that kind of determines whether we want to accept or reject the particular run. Depending on the acceptance, we perform a correcting displacement, if you want to, depending on the measurement outcome. And the state that we want to consider as the output state is then the state of the first mode, conditioned on acceptance. And now we similarly define the heralding state complexity, now depending on some acceptance probability threshold as the minimum number of elementary operations among all heralding preparation protocols that accept at least with probability p and prepare an output state that is epsilon close to what we want. Okay, so as a warm-up, it's a very simple warm-up. We can consider the preparation of coherent states. It kind of illustrates how the state complexity also depends on the set of operations that we allow. So let's say we want to prepare this coherent state D, being a displaced vacuum state by some vector in phase space. And if we only allow for constant strength displacements, kind of the best thing we can do is decompose this displacement unitary into constant strength versions thereof. So what we do is we basically start from a vacuum state and then shift it one by one in phase space until we reach the desired coherent state. And it's easy to see that this basically requires norm of D, many operations. So if we additionally allow unitaries generated by quadratic Hamiltonians, so in particular squeezing, we can actually do much better. So to see this, we note that a displacement in position, for example, can be rewritten as a squeezing operation followed by some constant strength displacement, followed by the unsqueezing. And so if we write the squeezing again or decompose it in constant strength versions thereof, what we do is we basically squeeze the vacuum more and more, we shift it, and then we unsqueeze it in order to generate this coherent state. And in the last step, we just rotate in phase space by an appropriate angle, which is by definition a constant strength operation. And if you do the calculation, you see that this only requires logarithmically many operations in the norm of D. So we can ask, is this actually optimal, or can we do better with the set of operations that we allow? And to answer this question, we kind of note that the energy of the coherent state is basically quadratic in the norm of the displacement. And on the other hand, these elementary unitary operations are moment limited, meaning that applying them once can increase the energy only by an affine linear function. So in particular, if we start with this initial state and applying a sequence of size t, the energy can grow at most exponentially. And so only from energy considerations, we can see that we need at least logarithmically many operations. So this gives a lower bound, and combining with the concrete preparation protocol, we've fully characterized the complexity of this coherent state for its exact preparation. Okay, so with this in mind, we can turn to a more complicated, namely a non-Gaussian state, the so-called GKP states. So formally, they're defined as the unique eigenstate of the two displacement operators, SP and SQ, so shift by 1 in position and a shift by 2 pi in momentum. And okay, so formally it can be written as the superposition of delta functions, but it's of course not a physical state because it's not normalizable. So an appropriate physical approximation is this two-parameter family of states, depending on these parameters kappa and delta, where kappa determines the width of the Gaussian envelope, and delta basically determines the width of the individual Gaussian peaks. Okay, so let me say that these GKP states are of high interest in several use cases, mainly in the realm of error correction. So there's been quite some previous work on their preparation. And so in the literature, the figure of merit that has been considered so far were these effective squeezing parameters, which kind of measure how good these stabilization properties, so this shift invariance by SP and SQ, is satisfied. And importantly, a small effective squeezing parameter does not guarantee closeness and trace distance. But trace distance is, of course, the relevant quantity for quantum information processing. So the preparation protocol that I will show you in a second actually comes with rigorous fidelity guarantees in terms of the trace distance, meaning that in principle you can replace any GKP state by the output state of our preparation protocol. And yeah, so one application of this is like some other recent work where we use GKP states for factoring integers, and I think there will be a talk in the afternoon on this if you're interested. All right, so now let's come to the actual preparation of GKP states. So conceptually what we want to do, so we want to start from a vacuum state and then iteratively double the number of peaks, creating this rectangular envelope state, a so-called comp state. And in the last step, we want to equip it with a Gaussian envelope. Okay. So the peak doubling part is basically done by this unitary V that you can see here. So it acts on one mode, characterized by this bold wire, and one qubit that is shown in this gray wire. So it explicitly makes use of these qubit-controlled displacement operations. So in order to see its action, we can kind of look how it acts on a position eigenstate at an integer. So you see that if we apply it on this position eigenstate tensored by a plus state on the qubit, we generate 2 peaks stabilizing the qubit state. And so if we do it n times, we generate 2 to the n peaks. Of course, in a physical, meaningful way, we have to replace the position eigenstates by squeezed vacuum states. And so what we do is we squeeze this vacuum state, we apply this peak doubling once, we shift it in position, and then we keep going to generate this comp state that you can see here, having 2 to the n peaks. Okay, so as I said, in the next step, we want to equip it with a Gaussian envelope. So why is this important in the first place, you could ask? So these approximate GKP states have the nice property that they basically look the same in position and momentum space. So if you look at the Fourier transform of the state, it also has a Gaussian envelope and Gaussian peaks, basically, where kappa and delta switch their roles. And so this is a nice property which we want to preserve and which we want to have in a lot of use cases. So the envelope shaping is the adaptive part. Everything previously has been unitary. So in the first mode, we basically encode a vacuum state and squeeze it such that it resembles the envelope that we want to generate. And in the second mode, we have this previously prepared comp state. Then we apply the so-called bosonic sum gate, which adds the position of the second mode to the first. And then we perform a homodyne measurement on the first mode. So if you do the math, you see that the post-measurement state of the second mode after this measurement is actually just this comp state multiplied by a squeezed Gaussian, which is centered at the measurement outcome x. So if the absolute value of x is not too large, we can kind of correct for this by recentering this. So we do we perform a displacement depending on the measurement outcome. But of course, if x is too large, then recentering does not guarantee being close to the target state, because then the tails are no longer balanced, and we are far away from the target state in trace distance. Okay, so if you tweak the parameters right, so the number of repetitions of this peak doubling and the acceptance interval, so at what point we reject if we measure too far away from the origin, we find that for sufficiently small parameters kappa and delta, this protocol accepts with probability at least 10%, and the output state condition acceptance is basically polynomially close to our target state, requiring only logarithmically many operations in 1 over kappa and 1 over delta. So again, you can ask, can we derive lower bounds, or is this protocol optimal? So the idea is that if a circuit is too short, then it kind of fails to approximate the Gaussian envelope either in position or in momentum space. So a too short circuit will generate a state that is too strongly located around the origin. So this is kind of the idea. And a bit more technical, but I'm leaving out the details here. So if we, again, start from this initial state and apply a unitary sequence and denote rho, the output state of, let's say, unitary or heralding protocol, we want to use, again, these moment limits. So we want to use the fact that the energy can grow at most exponentially in the size of the unitary part of our protocol. And what we can do with this, we can actually lower bound the distance of this output state to the GKP state in terms of the projection on an interval from -r to r in position, and similar also in momentum space. And so crucially, the first term can be lower bounded in terms of these energy upper bounds, and the second part can be upper bounded easily by some tail bounds, because the GKP states have a Gaussian envelope, as I said. So what we find is actually that in some parameter regime, our protocol is actually optimal. So more precisely, if the tolerated error is smaller than the acceptance probability, then the heralding state complexity of the GKP state is fully characterized by this logarithm of 1 over kappa plus 1 over delta scaling. Okay. So yeah, with this, let me conclude. So as we've seen, this was a full characterization of the complexity of coherent and approximate GKP states. And importantly, I want to repeat that this preparation protocol actually comes with accuracy guarantees in terms of the trace norm. So this can be relevant if you want to use approximate GKP states for quantum information processing or for quantum algorithms. And there are also some open questions. So one open question is whether it's a general rule that every single mode state can be approximately prepared with a number of elementary operations that scales logarithmically with the energy of the state. This was true for the coherent state and also true for the GKP state. And another open question is how the statements change if we impose fault tolerance. So can we efficiently, or is there an efficient fault tolerant implementation of these preparation protocols, and what effects does it have to the fidelity guarantees? All right, thanks for your attention.
Any questions?
Thanks for the nice talk. What's the model of computation? Also missing some background on GKP codes. Why do you want to do this preparation?
So the reason why we want to have a preparation in terms of the trace distance is because we are looking into quantum computation that is based on CV states where we don't encode qubits, but we rather want to use the CV states as the primitive, as the computational primitive directly. Yes?
Would you like elaborate a bit more detail in how you split the singles peak into doublings and so on,
Yes.
and also how to shape the envelope, not like Gaussian or any envelope can be realized, or Gaussian, yeah.
Yes. Just give me 1 second to find the slide. Okay, so the peak doubling revolves around this unitary here. So it's kind of illustrated how it acts on the right-hand side on the position eigenstate, basically. So you can see that it generates 2 peaks at integer positions. So this is exactly what we want. And the qubit can be kind of recycled in each run.
And also the envelope part,
Yes.
can we realize like not just Gaussian but any envelope shape?
Yes. So the statement is true that this adaptive circuit acts as a multiplication by the envelope part, basically. So if you prepare a state in the first mode that encodes or that prepares any envelope that you want, it's still true that it is just the second mode multiplied by the envelope state, basically located at the measurement outcome x.
Okay, thank you.
Yes.
Hi, Lukas. Thanks for the talk. So it was completely clear. So you're using qubits as well as continuous variable states?
Yes, exactly.
Do you think you can do it without qubits?
So if you start from vacuum states, for example, then it's not possible with the operation that I said, because they're all Gaussian operations to prepare a non-Gaussian state, obviously. So we would have to introduce some other type of non-Gaussianity, for example, a cubic gate, so a gate whose Hamiltonian is basically a cubic in some quadrature. Yes.
Another question. Is it possible to implement such interaction between qubit and continuous variable with current hardware, or is there such platform?
You refer to whether the qubit-controlled displacements are actually feasible, or yes. So I think in superconducting circuits and in trapped 1, so in trapped 1, for example, the qubit is encoded in the electronic structure, and the CV part is an emotional degree of freedom. I think these are, I mean, I'm not an experimentalist, but I think it's definitely possible to implement these kind of gates, yeah.
Yes. To prepare GKP states for continuous variable optics, there are also methods that does not use qubits, such as Gaussian boson sampling method, or cat breeding, or using current nonlinearity, and so on. So does your method provide some implication on which methods will be promising for optics, or it's hard
Sorry,
to
can
say?
you repeat the question?
The question is to prepare CV optical for in continuous variable optics. There are several methods to prepare GKP states without using qubits, such as like Gaussian boson sampling and cat breeding and so on. So does your method give some insights or implication about which methods would be more promising than the others, or?
Yes. So one of the so previous preparation protocols, as I said, they don't satisfy any accuracy guarantee. They're mostly based on heuristics. So you basically prepare states, and you don't do envelope shaping. But a lot of protocols, they use the fact that you have like some binomial distribution over some displacement, and then you say that for a lot of repetition, you, following the law of large numbers, you basically get a Gaussian envelope. But so I think this is like the first protocol that comes with rigorous analysis. What is happening?
Okay. Yeah. Thank you for clarification.
Any further questions?
So I'm just wondering, so say I have like this some finite energy and I want, I pick like some coherent states and I want to take superpositions of these states. So can I just simply do that using your this doubling method? Is that like?
You mean like cat states, for example? Or?
Right, or like a generalization of that if I have like, like any finite number of
Yes, I think this peak doubling is actually possible to also use it for preparation of these arbitrary superposition of coherent states.
Okay. Say in addition, I take some of those coherent state and I decrease, like, so I have like this 2 levels of energies and I have like coherent states on like this lower level of energies and higher level of energies. So I have like kind of like concentric circle kind of structure. Can I, in addition, do that using some sort of envelope shaping? Is that, if that makes sense?
Yeah, I haven't looked into this, but yeah, maybe if you.
Okay, right.
Yeah, maybe we can discuss later.
Yep,
if you want to.
absolutely. Thanks.